For this lesson, we will begin looking at trig identities. We will look at the fundamental trig identities. So our objectives are to derive and use these fundamental trig identities to help us find exact values of trigonometric expressions. Before we begin, let's look at our three main trig functions, sine, cosine, and tangent, and their signs in the different quadrants. If we are looking at sine, we know then that if we are in quadrant 1, the value is going to be, or I should say the sign is going to be positive. Same goes for cosine and tangent. When we move to quadrant 2 here, the sign is still positive as that's our y value. Our cosine is now negative. Because our tangent is a combination of sine over cosine, the tangent will also be negative. So here we have quadrant 1. Here we have quadrant 2. Moving on to quadrant 3, now our sine is negative, our cosine is negative, but look what happens to our tangent. Sine over cosine, negative over negative, gives us a positive tangent. And then finally, in our fourth quarter, our sine is still negative, our cosine is positive, therefore our tangent will be negative. We will need to be cognizant of the signs of our trig functions as we move through the trigonometric unit. So keeping this in mind will be helpful. Let's look at some examples. What if we have a sine of theta that's greater than 0 and a cosine of theta that's less than 0? In what quadrant would we be focused on? Well, let's think about. Sine is only greater than 0 in quadrants 1 or quadrant 2. Cosine is less than 0 in quadrants 2 or 3. These overlap in quadrant 2, so our answer here would be quadrant 2. Go ahead and try the next two on your own. Which quadrant are these in? For the next one, sine of theta is less than 0, we know is down here in 3 or 4. Tangent theta less than 0 has to be here, has to be quadrant 4. For the last one, we have to decipher what cosecant is. We don't see cosecant here, but we know it's the reciprocal of the sine. Well, when is the sine greater than 0? 1 and 2. When is cosine theta less than 0? Only 2. So for this one, the quadrant is 2. Now let's go ahead and apply that to some problems. So what if we have a cosine of theta of -4/5? We want to find the exact value of the remaining trig functions. Well, we know that cosine can be negative in quadrants 2 or 3. So we have an extra piece of information to help us to draw this triangle. We know then the tangent theta has to be greater than 0, and we know that only occurs down here in quadrant 4. So the cosine of theta equal -4/5 means that theta is down here in quadrant 4. When we get a fraction like this, we don't always know where this should be, but now we do know. So we know that we're coming out here, and we can draw our right triangle out here in quadrant 4. This is a little different than what you've seen before in that you don't have 2 points to represent this point P here on the circumference. But you do have a ratio, a cosine ratio, and we know from right triangles that cosine is adjacent over hypotenuse. So in this situation, this right here would be -4, as we're in the negative direction for x. And our hypotenuse is always positive. So -4 and 5 here. Now we're in a position where we can use the Pythagorean Theorem to find this leg. This is a simple triangle in that you can see right now it's a Pythagorean triple, a 3, 4, 5. So we know this value is going to be 3 as well. However, notice that we are in the negative area for y, so this would have to be -3. Now we have our triangle based on this information in the correct quadrant. and we can go ahead and find the exact values of the remaining trig functions. We already know the cosine of theta that was given to us. The sine is going to be opposite over hypotenuse. The tangent is opposite over adjacent. That comes out to a positive 3/4, negative divided by negative. And then for our reciprocal functions, we can just merely take the reciprocal. Go ahead and try the second one on your own. See if you can draw your right triangle and find the exact value of the remaining trig functions. The first step would be to identify the correct quadrant. Well, in this example, tangent is negative. Tangent is negative in quadrants 2 and 4. But in which of those quadrants is our sine greater than 0? And since our sine represents our y values, that would be quadrant 2. So now we just need to label the legs. Tangent is opposite over adjacent. Opposite is here, adjacent is here. So there's a negative. Where does the negative go? It wouldn't go with the 1, it would need to go with the 3, as the y value is positive here. So now we can do Pythagorean Theorem to find our hypotenuse. We have 1 squared plus a negative 3 squared would equal our hypotenuse or radius squared. We would get 1 plus 9 is equal to r squared. Therefore, r squared is equal to 10. And if we go ahead and take the square root, we get a hypotenuse of the square root of 10. Now we're in a position where we can find the other 5 trig functions. Starting with sine, we have opposite over hypotenuse. We know we can't leave it like that. We need to rationalize our denominator. So we get root 10 over 10. Notice that this is a positive root 10 over 10. If we look at cosine, we have the same thing, only now we have negative adjacent over hypotenuse. So negative root 3 over 10. Again, we have to rationalize our denominator. We would get negative 3 root 10 over 10. We already have the tangent that was given. For cosecant, I would go all the way back here to 1 over root 10 and flip that. That way I don't have to re-rationalize my denominator by taking root 10 over 10 and flipping that. So let's get root 10 here. For this one, cosine, I would have negative root 10 over 3. And for my cotangent, I would have negative 3. So again, when I've gone back and I've taken the reciprocal of my key functions, I always want to check and see which one would be the best function to take the reciprocal of. The rationalized version would take me more steps. Let's move on to our main identity. This, if you recognize, is the equation of a circle. And remember, we're dealing with a unit circle. This comes from the Pythagorean identity of a squared plus b squared equals c squared, if you remember correctly. Now remember that in our unit circles, we have a value for h and k of 0, 0. Our unit circles are right on the origin. And our radius is equal to 1 in our unit circle. So let's start from this. Simplifying this to incorporate an origin of 0 and a radius of 1, we get x squared plus y squared equals 1. We know that to be true. Now if we think about our trig functions, x squared is represented by cosine. So we can say cosine squared of x, or some theta, plus the sine squared of x, or again some theta, will always equal 1 as well. That is a very important trig identity. It is a fundamental trig identity in which we can derive many other identities. Let me show you what I mean. Say we wanted to write this expression in terms of cosine. Well, we would say that the cosine of theta, cosine squared theta, is going to now be equal to 1 minus sine squared theta. If I wanted to write this in terms of sine, then I could say that sine squared theta is equal to 1 minus cosine squared theta. And from here, we can write a few other identities quickly. But let's go ahead and try some examples using what we have right here. Here's our first example. Sine squared of 20 plus cosine squared 20. What does that equal? Well, based on our sine squared theta plus cosine squared theta, we know that this simply just equals 1. How about this second one? Tangent squared theta minus 1 over cosine squared theta. A hint for how to do these is to remove fractions if you can. So 1 over cosine squared theta is the same thing as secant squared theta. So we can replace that with secant squared theta. But then you're saying, well, how is that going to help me? Let's go back to our identities and see if we can figure this out. Here's where we have to be creative. But we can start with our major identity, cosine squared theta plus sine squared theta. And I'm going to go ahead and write the sine squared theta first, based on what we're doing. But order doesn't really matter. So if we start here, we know that we need to get tangent, if we go back to our problem, and secant. So how can we derive that from this fundamental identity? Think about what tangent is. Tangent is sine over cosine. So what if we take and we divide all of these trig functions by cosine squared theta? Let's see what we get. This one becomes tangent squared theta. This one becomes 1, and 1 over cosine squared theta is equal to secant squared theta. Now if we look back at our problem, this is looking a lot more familiar. We have now tangent and secant. In our problem, though, we have tangent minus secant. So what can we do for that? Well, we can subtract the secant to the other side and move the 1 to the other side as well. So we would get tangent squared theta minus secant squared theta is equal to -1. Now if we look at our problem, that's what we have. Tangent squared theta minus secant squared theta, we know is equal to -1. And that's one example of how we can take the fundamental trig identity and create other trig identities. Let's go to this third problem. Tangent of 40 minus sine 40 over cosine 40. Well, again, remember what I was saying. We don't like fractions, so let's get rid of this fraction, and that can now be tangent of 40 degrees. Well, the tangent of 40 minus the tangent of 40 is just 0. Let's look at our next example. We have the cosine of 400 degrees times the secant of 40 degrees. We could look back at our trig functions and see how we can get secant, but hopefully your brain is thinking, well, secant is just 1 over the cosine, so I can change this to 1 over the cosine of 40 degrees. Now if I multiply, this is the same thing as cosine 400 over 1, I will get the cosine of 400 over the cosine of 40. Now be careful that you don't try to divide these angles, because the angles in and of themselves don't mean anything. The cosine of 400 has a distinct value, just like the cosine of 40. So right now, we can use our periodic properties to simplify our numerator a little bit. We can subtract 1 whole period, and we would end up with the cosine of 40 over the cosine of 40. We know that the numerator value will be the same as the denominator value, and therefore the answer here is just going to be 1. Let's look at our final example. If you'd like to try this one on your own, go ahead and pause the video and see if you can come up with this answer. For our last problem, there's a couple of ways that we could do this quite easily. If we look back, we have secant. We could just subtract the tangent and we would know that we would be left with 1. That's a quick way because we have just used that identity for this problem up here. We could also take this and we could turn it into its basic trig functions. We know that secant is the same thing as 1 over the cosine, so we could rewrite it this way. We also know that tangent is the sine over the cosine. Notice that we have common denominators, so we can rewrite this as 1 minus sine squared theta all over cosine squared, I should say 18 degrees, since we do know theta in this problem. From here, we can look back and see what 1 minus sine squared is. 1 minus sine squared is cosine squared. So we can replace the numerator with cosine squared of 18 over our denominator, which is also cosine squared 18, and again we know the value is 1. So either way, whatever is the most simplest way for you to figure out these exact values based on these identities, that's what you should do. So make sure in your notebook that you have this fundamental identity and that you've rewritten it in a few forms. As we move forward, we'll be adding more forms to our library. This concludes our lesson on the fundamental trig identities. At this point, you know how to derive and use the fundamental trig identities to find exact values of trigonometric expressions. You can also use the different quadrants and the signs in order to help you further find exact values for trig functions.